Hi students, good morning. How do you do? I hope that you have, first of all, you are well and you have solved the problems and solved examples for the previous lecture. Good. Okay. Today we will study the third part of this course. We will study the pre-Maxwell's equations in electromagnetism inconsistency. And also we will study the displacement current. And also we will study the Maxwell's equations in integral form and differential form. Also we will study electromagnetic wave equation and Helmholtz wave equation. Also we will see the solution of wave equation and solving some example. The general form, basically we have four main basic Maxwell's equations. We have in two forms, integral form and differential form. As you can see in this slide, the left part, this left part for the integral form of Maxwell's equation, and the right side here, these are the differential form of, or the time harmonic form of Maxwell's equation. First of all, we need to know that we have four Maxwell's equation. The first Maxwell equation is Gauss law, and the second Maxwell equation is the magnetic charges do not exist, and the third Maxwell's equation is Faraday's law, and the fourth Maxwell's equation is Ampere's law. Also, I would like to remind you that the very important two equations in the electromagnetic field, which is the electric field density, D equal epsilon E, and the magnetic flux density equal mu H. Now we will solve and we will see that for the Gauss law, the closed surface integral of D dot ds equal the volume integral of rho dv, which is the Q, which is the charge enclosed by the closed surface. In the differential form, divergence of D equal rho, the charge, the total charge enclosed by the enclosed surface. And also the second Maxwell's equation, which says magnetic charges do not exist, which is we have seen in the previous lecture, the closed surface integral B dot ds equal to 0. This is integral form, but in differential form, divergence of B, which is 0. So there is no enclosed magnetic charge. The third Maxwell's equation, which is Faraday's law, the closed contour integral of E dot ds equal to minus surface integral of the partial derivative of the magnetic field intensity with respect to time dot ds. In the differential form, the curl of E equal minus dB by dt. And Ampere's law, which is the fourth Maxwell's equation, the closed contour integral of H dot ds equal J dot ds. And in the differential form, curl of H equal the partial derivative of D with respect to time plus the current density. Surprise! These formulas are inconsistent. The pre-Maxwell's equation inconsistency. Inconsistency comes about because a well-known property of vectors, divergence of curl equal to 0. This is identity which gives the inconsistency condition. Apply this to Faraday's law, for example. We put divergence of curl of E, and we will substitute instead of curl of E by minus dB by dt will be minus partial derivative of divergence of B. And you know that divergence of V equal to 0. The left side is to 0 because of the above noted property of vectors. The right side is 0 because divergence of B is 0, no magnetic charge. If you do the same operation to Ampere's law, also you can apply and you will have a trouble. Now we need to understand how displacement current came to be. You remember that divergence of curl of H equal divergence of J over mu naught. The left side is 0, but the right side is not generally 0. If one applies Gauss' law and the continuity equation, divergence of J plus the partial derivative of the volume charge density with respect to time equal to 0. The above equation becomes, now we apply divergence of J equal minus partial of rho with respect to t, and which is equal minus partial of, we substitute rho by d epsilon divergence of d, or epsilon or divergence of d, because here we substituted d by epsilon e for free space. And this also, if you take the divergence out, will be minus divergence of epsilon naught partial derivative of e with respect to time. So Maxwell's equation become consistent here. If we rewrite Ampere's law again, we will find curl of H equal J plus the partial derivative of d with respect to time. And the partial of d with respect to time, we call it the displacement current. So you have seen how we get the displacement current due to the variation in the electric field intensity or electric field density with respect to time. In this case, a changing electric field induced a magnetic field opposite. So here, the changing electric field produces a magnetic field. Now, also, we would like to show you the Maxwell's equation, and you have seen in this slide, this is a picture of James Clerk Maxwell, who discovered and put the 4 Maxwell's equation in integral form and in differential form. And these are, as you have seen, for integral form, for Maxwell's equation with d equal e in general, epsilon e, b equal mu h, and this is the differential form of Maxwell's equation. Now also in this slide I will show you the electromagnetic wave. Here you can see the electromagnetic wave is composed from 2 waves, the electric field wave and the magnetic field wave. The blue is the electric field and the red is the magnetic field wave. These 2 waves are perpendicular to each other, and these 2 are also perpendicular to the direction of propagation in the direction of z. And lambda is the wavelength of the sine wave, okay, which gives you the frequency of the signal of the electromagnetic wave. Also, we will study the plane wave solution. Will be more easier to solve the wave equation and Helmholtz equation. And the solution of the plane wave is given by E of r comma t. Here E, electric field, is function of the distance r vector with and time, which is equal E naught e to the j k dot r minus j omega t. And also B of r comma t equal b naught e to the j k dot r minus j omega t. This is the general form for the solution of the wave equation for the plane wave solution. Here we assume no sources and vacuum and also non-conducting medium. I will take example. If the electric field in vacuum is E equal AX E naught cosine omega t minus K1, what is H? Solution. From Faraday's law, 215, mu naught partial of H dt equal minus curl of E and equal AZ partial of EX with respect to Y, which is equal AZ K E naught sine omega t minus KY. Using 214 for the curl operator, integration of this equation with respect to time will be H equal minus AZ K E naught over mu naught omega multiplied by cosine omega t minus ky. Also, we will show next another example. Does the electric field in vacuum E equal ax E naught cosine omega t minus kx satisfy Maxwell's equations? Under what circumstances would this E satisfy the equations? Solution. This electric field does not satisfy Gauss' law for vacuum, which requires divergence of D equal rho, which is equal to 0. It satisfies Gauss' law only for non-zero charge density. Rho equal divergence of D, which is equal epsilon partial of Ex with respect to X, partial of this epsilon naught E naught cosine omega t minus Kx with respect to X, which is K epsilon naught E naught sine omega t naught K, which is not equal to 0. So it does not satisfy Gauss' law. To satisfy the remaining Maxwell's equation and conservation of charge to 119, there must also be a current J density does not equal to 0, corresponding to rho and J equal sigma E. And in this case, G is not equal to 0 because J equals sigma E, which is E is not 0 and sigma is not 0. Now we need to study the electromagnetic waves in the time domain. Perhaps the greatest strength of Maxwell's equation was their ability to predict in a simple way the existence and velocity of electromagnetic waves based on simple laboratory measurements of the permittivity and permeability of vacuum. In vacuum, the charge density rho equal J and equal to 0. And so Maxwell's equation becomes curl of E equal minus mu naught partial of H with respect to time, which is Faraday's law in vacuum, and curl of H equal epsilon naught partial of E with respect to time, which is Ampere's law in a vacuum, and divergence of E equal to 0, which is Gauss' law in vacuum, and divergence of H equal 0, which is divergence of B equal to 0, or divergence of D. Also, this is Gauss' law in vacuum for magnetic field. We can determine H from these equations by computing the curl of Faraday's law, which introduces curl of H on its right-hand side. So Ampere's law can be substituted. Curl of E equal minus mu naught partial of curl of H with respect to time, which is equal minus mu naught epsilon naught partial second partial derivative of E with respect to time. Using the well-known vector identity, see Appendix D, curl of A, which is the gradient of divergence of A minus gradient square A, this well-known vector identity. And then using 2, 2, 3 to eliminate divergence of E, 2, 2, 5 becomes the electromagnetic wave equation, often called the Helmholtz wave equation. So the Helmholtz wave equation is the electromagnetic wave equation, gradient square E minus mu naught epsilon second partial derivative of E dt equal to 0, which is Helmholtz wave equation. And you can see here, this is the vector gradient square of E. And the solution to this wave will be E of R of t equal E of Z minus Ct, Ax Z minus Ct. And where the arbitrary function Ex of Z minus Ct might be that illustrated in figure 2 at time equal to 0. This figure, so you can see this figure, 2, 2, 1, the arbitrary electromagnetic wave propagation in the Z direction. This is at t equals 0. This is at t greater than 0. And this is Ex of Z2 of t. So this is the wave equation. The students, we have studied in this section the pre-Maxwell's equation and electromagnetic wave inconsistency, displacement current, and Maxwell's equation, and Helmholtz equation or the wave equation. Thank you for your kind listening.